Szeged. I am Stamatina, immediate past chair of Young Szeged, and it's my pleasure to welcome you all on our talk on recent advancements on performance-based design and seismic risk assessment of steel structures. Before we get started, please let me go through a few housekeeping rules. Please can everyone keep their videos off and microphones on mute during the seminar. We will have a Q&A session after all presentations, but please feel free to type your questions in the chat at any point. Please note that the seminar is being recorded and will be uploaded onto our YouTube channel. Therefore, by dialing into this event, you consent that any views or information you share being made public. Before introducing our speakers, I would also like to bring to your attention two things related to Szeged. The first one is the Szeged 2023 conference, which will take place during 14th and 15th of September this year in Cambridge. You can visit the conference website to book your ticket and benefit from the early bird rates, which will be available until the end of June. I'll put the conference website at the chat later on. The second item is the Szeged Fund. Applications are now open and the deadline is end of July. Applications for an award of up to £1,000 will be considered, and I remind you that the only criterion for applying is a valid Szeged membership, which is also free for students. So, going back to the event itself, in this seminar, we have with us three speakers from the École Polytechnique Fédérale de Lausanne, Professor Dimitros Lignos, Dr. Andronikos Skiadopoulos, and Dr. Nenad Bijelić. Our talk will start with Dimitros Lignos, who is a full professor and chair of the Civil Engineering Institute at the EPFL. He holds an MSc and PhD in structural engineering from Stanford University and a diploma in civil engineering from the National Technical University of Athens. Professor Lignos' research involves integrated computational modeling and large-scale experimentation for the fundamental understanding and simulating of earthquake-induced collapse of steel and composite steel structures. His awards include, among others, the 2022 Raymond Rizzi Research Prize and the 2019 Walter Haber Prize from the American Society of Civil Engineers. Our second speaker will be Andronikos Skiadopoulos, who is currently a postdoc researcher in the Resilient Steel Structures Lab at the EPFL. He holds a PhD in structural engineering from the EPFL and a diploma in civil and environmental engineering from the National Technical University of Athens. His research focusing on modeling and experimentation of steel structures subjected to extreme hazards. He is the recipient of the 2022 Raymond Rizzi Research Prize from the American Society of Civil Engineers and the 2022 Outstanding PhD Thesis Distinction in Civil and Environmental Engineering from EPFL. The last speaker for today will be Nenad Bijelić, who is a postdoc scholar in the Resilient Steel Structure Lab at the EPFL. He obtained his PhD and MSc from Stanford University and his bachelor's from the University of Zagreb in Croatia. His PhD research was supported by the 2012 International Fulbright Science and Technology Award and the 2015 Shah Family Fellowship on Catastrophic Risk. His research is in the area of probabilistic risk modeling and natural hazard engineering, focusing on dynamics of nonlinear systems and application of statistical and machine learning tools. Dr. Bijelić co-convened a session on theory-guided machine learning approaches in earthquake engineering at the 2021 Earthquake Engineering Research Institute annual meeting in the US and is currently organizing a technical session at the upcoming World Conference on Earthquake Engineering in Italy next year. So I think it's fair to say that we are all very curious to hear more about your research at the EPFL. So without further delay, I will hand over to our first speaker, Professor Lignos.
Okay, thank you very much. Okay, let me share. Okay. Okay. Okay, can you see my screen?
Perfect, came through.
Okay, so thank you very much for the nice introduction. So I guess my role here is to be the one who is going to talk less. So essentially, I plan to show you some of the activities we are working on in my lab at EPFL. And the overall theme of today's talk is recent advancements in performance-based design and seismic risk assessment of steel structures. I guess before I start, I would like to thank the Society for Earthquake and Civil Engineering Dynamics for the nice invitation, the kind invitation. And I'd like also to thank the Swiss National Science Foundation, as well as Nippon Steel Corporation, for sponsoring some of the work to be presented today. I guess a little bit on what we do. Earthquake, as you know, earthquake activity worldwide is quite significant, and in several occasions, major earthquakes we have witnessed vanish complete cities, as well as villages such as the one here in Italy. I guess what's striking in this some of these problems is that if you look at some of the key statistics worldwide, if you haven't realized, essentially earthquakes cause about 28,000 casualties per year. And I guess another aspect that maybe we tend to forget is that we see that there's displaced population, which is about 300,000 a year. So if you are from, if you have been to Lausanne, that's essentially the population around Lausanne, and it's quite distracting. So the primary focus of what we do is we try to understand why buildings collapse, and then if we understand why buildings collapse, then we can formulate different ways so that we can alleviate these problems and potentially, hopefully, reduce these numbers to the extent possible. So for this reason, I will go through I will review the underlying physics of the problem. So if you have a building that is subjected to an earthquake, I mean, I guess you all know this from Structural Dynamics 101. So you basically have displacements, and then if you go through the equation of motion, you have that the external force is simply equal to inertia forces plus damping forces and the restoring forces. So a lot of the things that we do essentially relate to the last term here, which is highly nonlinear. And in particular, we are essentially trying to develop models where we can capture some of these nonlinearities. And when you are dealing with collapse, this is an example from the Kobe earthquake in Japan on a steel building that collapsed the first story mechanism. Essentially, what you need to do is essentially you have to capture well material nonlinearities, but more importantly, nonlinear geometric instabilities that generally cause softening. And essentially these, for typical structural components, will look like the figure on the left for a column. But if you're looking on wind turbines that are popular these days, collapse due to extreme loading, again, would be linked to this type of instabilities. Now, the problem is that if you have good models, there is scarcity on available data at large deformations, simply because it's hard to monitor collapse. You must know when it happens. And then if you try to do this in a laboratory environment, it's also hard to do it because you need maybe special equipment, but also safety is another aspect because we are dealing with instabilities. So what we do here at EPFL, in my group, essentially we try to develop models that we capture these effects. These models essentially are models of different fidelities. Then we try to design control experiments so that we can validate some of these models, but also understand how instabilities interact together and essentially could compromise the system's behavior. Then we try to bring this at the system level and develop methods for simulation-assisted infrastructure assessment, where we also try to look at some of the financial aspects related to earthquakes. And I guess what's interesting here, at least what it's more interesting for me, is how can we use this knowledge to develop concepts for instability-free performance, where essentially we'll try to minimize uncertainties and generally lead to better performance of our infrastructure systems. So I'll just go through some indicative work we've done on this. I guess the first one relates to models that I described. So we've been working on this over the last 15 to 20 years. Some of our original work is related to concentrated plasticity models. But more recently, we've been looking also into a continuum, such as fiber models and fully continuum systems with some coupling techniques so that you can expedite computations. So here you should know that limitations depend on the modeling option, and there is a trade-off between simplicity, so basically models on the left, computations and modeling uncertainties, while moving to the right. So if I take a little bit, if I say a few words on the first one, on concentrated plasticity models, usually you may be familiar with the modified Ibarra-Medina-Kravinkler model, which is essentially a model that captures softening. It's computationally efficient, and we've calibrated it with over 500 to 1,000 experiments of different components. But the problem is that it requires large data sets for calibration, so you must have data at large deformations, and usually we are lacking this type of data. And also, these models do not always preserve physics, and this is why, for instance, when you're looking at predicted versus measured quantities related to plastic deformation capacity, you see that there could be quite a bit of variability here. So for this reason, some of our latest work relates to macro models, where we essentially what we do here is we try to couple models of different fidelities, such as continuum, with a beam column element through methods for domain coupling. And essentially, we try to use more expensive models for regions of elements that matter, such as the dissipative zone. And here, of course, the secret sauce would be how to model accurately imperfections so that you can trigger instabilities correctly, as well as having reliable constitutive formulations at the material scale, and so that you can capture the material response accurately. Now, the models I showed, as well as others, are all available in the open source platforms such as OpenSeas, but also in commercially available software such as Abacus. And essentially all the source code is made publicly available through the lab's website. Now, as I said, models are great, but you also need experiments to validate the models, but also understand the physics behind some of these instabilities I showed. So basically here at EPFL, we have developed a customized setup that essentially allows for physical testing of steel structures with emphasis at large deformations. And here you see, for instance, an example of a 10-meter long frame, a 2-bay, where we try to understand the role of framing action and slab prior to collapse, and how complex instabilities such as local buckling that you see here, as well as crack development and propagation, could compromise the system ability to carry lateral load. So here note that this frame was subjected to lateral load up to about 20% drift. And also we're able to acquire useful data with sophisticated instrumentation, such as digital image correlation, as well as other type of instrumentation, so that we can acquire data to validate some of the models I showed earlier. Moreover, we have looked extensively on the behavior of other elements, such as columns, and this is an example from work of former student who is now in UK, Professor Elkadi. And here you see how, for instance, a column under extreme loading experiences shortening, and the model on the right, how it can capture well the response. Now, now we have a centralized data policy, and we support open science. So all the data we have acquired, as well as others we have collected over the last 15 years, is made publicly available through our website here. That allows also for different visualization features, depending on what you are looking for. and generally allows for easy navigation if you're looking for a particular test. And this relates to connections, columns, braces, as well as materials that we made recently available. Now, before I finish it, we try to bring this at the system level so that we can enable simulations so that we can eventually compute the collapse risk of buildings such as the 8-story building I'm showing here. And this computational framework essentially allows you to bring in historic data, also be able to do large-scale parametric simulations, and you can eventually trace collapse for different ground motion records. And eventually you can also incorporate statistics and essentially quantify the probability of collapse if you want to formulate policy or if you want to see the influence of uncertainties in the collapse risks, such as the one that I show here. Then the last thing is that we try to link this with life cycle costs. So essentially, if you have a specific asset, we have developed software that is made publicly available that allows for risk, loss, and life cycle analysis. And essentially, for different scenario earthquakes, you are able to do loss deaggregation and see where your asset essentially should be retrofitted or what kind of components could be potentially vulnerable after a scenario-based earthquake. Now, I mean, one question I tend to ask myself every, few years is where to go from here. So generally, if I'd like to answer that question, I'd like to quote Professor Ed Wilson, longtime faculty at UC Berkeley, where he once said that instead of trying to develop more complex models to capture the variability of structural response, then we should be designing structures that are less sensitive to uncertainty. So having that in mind, what we try to do is that we try to ask the question if we can leverage knowledge that we acquire from what I showed to prevent instabilities, but through conventional design concepts, so that engineers can actually use them relatively easily. And with that, we can reduce model uncertainty, but at the same time, when it comes to risk quantification or risk assessment, we are trying to see if there are ways to reduce computational burden by using physics-based models such as the ones I showed, but running simulations more wisely. So with those in mind, I would like to pass it to today's talk. So Dr. Skiadopoulos will present new concepts that defy the current paradigm in steel moment resisting frame designs to achieve instability-free performance at large deformations. And with regards to the second part that relates more to risk quantification, Dr. Nenad Bijelić will go through new methodological developments on how you can leverage data-centric surrogate modeling with physics-based models to inform more efficiently collapse risk assessments of steel moment frames. So with that, I'd like to thank you very much for your kind attention, and I guess we will hold questions at the end. So let me stop it here and pass it to Andronikos.
Okay, so here we are. Can you see my screen?
Yes. Came through.
Okay, hello everyone from my side, and thanks a lot for all for being here for this lunchtime seminar series. I would like to thank the organizing committee of SECED for the invitation to this seminar series, and I'm also happy to see good friends from our bachelor studies at the National Technical University of Athens joining this event. So today's presentation is entitled Welded Moment Connections with Highly Dissipative Panel Zones for Enhanced Seismic Performance of Steel Moment Frames. In capacity design, steel moment resisting frames in elastic deformations are mostly concentrated in the steel beam ends and the first story column fixed ends. And design principles after the 1994 Northridge earthquake and the 1995 Kobe earthquake limited the participation of the column web panel zone in participating in the earthquake-induced energy dissipation. Therefore, local buckling is anticipated in the steel beam ends at modest lateral drift demands, as highlighted in the right figure of this slide. Here we see a typical beam-to-column connection test of a welded moment connection, where in the left figure we see the global response of the beam-to-column connection. On the right side we see the panel zone response. And what we observe here is that at 4% story drift ratio, the connection loses more than 20% of its load carrying capacity. And this is because of the fact that beam local buckling initiated at 3 to 4% story drift ratio, as shown in the far right figure. However, if we assume a nominally identical beam-to-column connection in terms of dimensions and cross sections, while in this case we intentionally weaken the panel zone shear resistance by removing the doubler plates that are adjusted to the column, what we see here is that the connection achieves a very stable hysteretic response at 4 and even at 6% story drift ratio. And this is because of the fact that in this case we enable the inelastic deformations of the panel zone, and therefore we take advantage of the beneficial aspects of panel zone shear yielding. This connection reduces the potential of structural repairs due to the delay of beam local buckling, as you can see characteristically in the bottom right, far right figure. To give some historical input to the beneficial aspects of panel zone, shear yielding were identified back in 1970s by work of Professors Kravinkler, Bertero, and Popov and UC Berkeley. And from the small-scale beam-to-column connection test they conducted, they found out a very stable hysteretic response in the connection level because of the fact that we employ the beneficial aspects of panel zone shear yielding, which is a very stable hysteretic mechanism, as on the far right figure. However, the main reason why an elastic panel zone design is not promoted in current pre-qualified connections in the design norms is the increased fracture potential that may be associated with increased panel zone distortions. The increased fracture potential of such a connection methodology was highlighted in the connection fractures of the 1994 Northridge earthquake. As shown in the middle figure, connections at that time were not able to withstand lateral drift demands exceeding 2% story drift ratio, which is equivalent to the design basis earthquake event. So as you can imagine, this is an unacceptable performance, unanticipated performance. And this unacceptable response is because of the fact that brittle fractures were identified in almost half of the connections that were respected at that time, as shown in the far right top figure. The primary reasons behind the inadequate performance of the connections at that time are the presence of the weld backing bar that was associated with the notch condition that increased the fracture potential in the critical beam flange to column face connection, the weld access hole geometry that was concentrating stress and increased stress and strain demands at that region, and finally the inadequate toughness of the weld material that was utilized at that time. For all these reasons, in elastic panel zone design is not promoted in current design norms. The lessons learned from the 1994 Northeast earthquake led to what we have today as pre-qualified weld moment connections, as characteristically shown in this schematic here. To ensure limited deformations within the panel zone, doubler plates are often imperative. Note here that these doubler plates are welded to the column web, and therefore the shear resistance of the column web panel zone is increased, and we ensure almost elastic panel zone and almost elastic panel zone response. This connection typology features an optimized access hole geometry to minimize stress and strain concentrations in this region, and therefore to delay the onset of fracture at that region, and also a weld metal with increased toughness requirements. Finally, with regard to the welded detail, after the execution of the complete joint penetration weld, the temporary backing bars that are placed in that region should be removed. Then this region should be back-gaussed, and finally, fillet weld reinforcement should be placed at that region, as noted by the top arrow, to close any potential cracks in this region. This process is deemed to be time and resource consuming. To assess the beneficial aspects of panel zone shear yielding, we collected a database of more than 100 inelastic beam-to-column connections that we also made publicly available. The database features different connection typologies that date back to 1970 to 2017 or even to present, and includes variable connection geometric as well as material characteristics. If we look at the fifth column of this parallel plot that concerns the panel zone response, we saw with gamma max over gamma y the attained panel zone shear distortions normalized by the panel zone shear yielding noted in this presentation as gamma y. And what we see here that is this collection, this database collection that we have includes panel zones that far exceed the current allowable limit. And therefore, we can study the effect of inelastic panel zone shear yielding in the connection performance. Note here that this dataset, together with several other databases and models for design and assessment of steel structures, are shared in the given QR code. From the collected data that I described before, we calculated the probability of a connection experiencing fracture. As you can see here from the bivariate log normal distributions, where the normalized attained shear distortions and the story drift ratio within the connection explain the probability of connection fracture. So what you can see here is that qualitatively, once we increase the deformations in the connection or the panel zone, the probability of connection fracture qualitatively increases. However, if we look at the story drift ratio of 4%, which is characteristic to the maximum considered earthquake event, then we see that by increasing the target panel zone distortion from 4, which is currently the allowable limit in the design norms, to, for instance, 10 gamma y, then the probability of connection fracture practically does not change. So what this shows, and the research question that arises now is by how much could we potentially push the inelastic panel zone distortions in terms of seismic design. Finally, to potentially exploit the beneficial aspects of panel zone shear yielding, a reliable panel zone model is imperative. And by utilizing the test data that I described before, we compare the prediction of the American code as VP, and we normalize it with the experimentally assessed panel zone shear strength as VPM. So what we see is that this ratio tends to be to 1.4, which means that the American code overpredicts the real panel zone shear strength at 4 gamma y by more than 40%. And this is especially critical when we utilize panel zones with thick column flanges. Therefore, to mobilize the panel zone in seismic design, a more robust panel zone model should be first potentially developed. This brings us to the outline of this presentation, which is the development of a robust panel zone model for the seismic design of steel moment resisting frames, panel zones. Second is the development of simplified weld details for welded connections with highly inelastic panel zones, and then to the full-scale beam-to-column connection experiments to validate the previous concepts. And finally, since there is a concern that inelastic panel zone design may compromise the seismic stability of steel moment resisting frames, we conducted system-level simulations with inelastic panel zones to investigate this concern. Moving forward to the panel zone model development. Panel zone models historically comprise 3 branches, with the first one being the elastic one. So this one assumes uniform panel zone shear yielding at Vy, where the contribution of the column flanges is disregarded. With regards to the panel zone elastic stiffness Ke, this is computed based on the shear deformation within the panel zone, where in this case the bearing deformation mode is disregarded. The second branch is the post-yielding branch, and this was calibrated based on limited experimental data with column flanges with thicknesses less than 40 millimeters, and therefore Therefore, there is a limitation with regards to the column flange thickness. With regards to the third branch, typical value of the post 4 gamma Y panel zone stiffness equals to 3% the panel zone elastic stiffness. From the collection of the test data described before, the experimental panel zone elastic stiffness is deduced from the first cycle envelope as shown on the left side of the slide, where we have a typical response of a panel zone, where in the vertical axis we see the panel zone shear, and the horizontal axis we see the normalized panel zone shear distortion. So from the first cycle envelope of the hysteretic panel zone response, we extract the panel zone elastic stiffness, and we call it KEM, which is shown in the horizontal axis of the right side figure. In the vertical axis of the right figure, we compare the predictions of available panel zone model equations. What you see here is that available models like the American code or the Kiemen-Engelhardt mode tend to overpredict the panel zone elastic stiffness by more than 20%, and this is because of the fact that these models assume shear deformation dominance within the panel zone. However, models that kind of explicitly account for the bending deformation mode within the panel zone provide a better performance in terms of predicting the panel zone elastic stiffness. Regarding the panel zone shear strength at 4 gamma Y, again, from the collection of data that I described before, we deduce the panel zone shear strength at 4 gamma Y, which is the limit in the American code. And typical panel zone models are similar in nature with that of the American code. And as also described before, these tend to overpredict the panel zone shear strength by more than 40%, especially when thick column flanges are utilized in the design. It should be noted here that Eurocode is doing even worse job in predicting the panel zone shear strength, but this is not shown here due to brevity. To address the limitations of available panel zone models, we developed a more robust panel zone model that is based on continuum finite element analysis. Due to time brevity, I'm not going to go through the modeling details, but these are found in the paper given below. That was written from me, Professor Elkadi in the University of Southampton, and also Professor Lignos here at EPFL. The comparisons between the test and the continuum finite element analysis models are highlighted here in this slide. On the right side, on the left side, we see the connection, global connection response in terms of column shear force versus story drift ratio, and on the right side, we see the panel zone response in terms of panel zone shear force in the vertical axis versus panel zone shear distortion or shear angle in the horizontal axis. What this slide suggests is that the modeling assumptions we assumed are capable of capturing accurately both the global as well as the panel zone hysteretic responses, and therefore these modeling assumptions are utilized hereinafter for the panel zone model development. So first, we proposed an elastic stiffness that accounts for both bending as well as the shear deformation mode within the panel zone. And these deformation modes are assumed to be working in series, as shown by the given equation of Ke. Note here that this is especially critical for panel zones with aspect ratios higher than 1.5, where the bending deformation mode may be critical. By comparing the proposed panel zone stiffness with the measured one from the experimental data that we collected, we see that the proposed model captures very accurately the elastic stiffness. Regarding the panel zone shear strength, we looked at realistic shear stress distributions in the panel zone of variable geometries, as characteristically shown by these two schematics on the left top side. What we observed is that for stocky panel zone geometries, the flange contribution, which is, as I described before, disregarded in available models. So the flange contribution in the panel zone shear strength may be really considerable, especially for stocky panel zone geometries. Therefore, we proposed updated equations that consider for both the web as well as the flange contribution. And these equations were benchmarked at gamma Y, which is the panel zone shear distortion at yield, 4 gamma Y and 6 gamma Y. comparisons with available test data reveal that the proposed model increases the accuracy and decreases the variability in predicting the panel zone shear strength at 4 gamma y, and similarly for other distortions. And this is especially critical for thick column flanges of, let's say, 70 millimeters, as highlighted in the right side of the slide. In this video, we see an FE simulation result of an interior subassembly that utilizes very thick column flanges of 72 millimeters. And on the left side, we see the shear force versus shear distortion response of the FE and the test data, and superimposed are also the predictions of the American code and the proposed model. What we see in this slide is that the proposed model is capable of predicting very accurately the panel zone elastic stiffness, as well as the panel zone shear strength, regardless of the panel zone shear distortions. So what we can conclude from this slide indicatively is that these results show us that we can potentially rely on panel zone designs that are up to 6 gamma y at least. Moving forward to the development of simplified weld structural detailing rules for welded moment connections. To potentially simplify the welded moment connection detailing, a conventional backing bar is first assumed as utilized before the 1994 Northridge earthquake, as shown on the left side of the slide. What we see on the right side in the vertical axis is the J integral, or you can think about it as the fracture potential of the connection. And the horizontal axis, you will see the story drift ratio of the beam to column connection. By comparing the fracture potential with the typical fracture toughness of weld electrodes utilized currently in the seismic norms, we see that such a connection is not able to withstand lateral drift demands exceeding 2%, which, as I also said before, it's characteristic of the design basis event, earthquake event, which is not an adequate performance to have. The primary reason for this is that once we have a backing bar in place, this may impose a crack that penetrates through the beam flange thickness, and therefore the beam loses the maximum moment capacity that is able to sustain, since now less flange thickness is utilized in sustaining this moment. Motivated by this, we came up with a bevel backing bar geometry that basically keeps any potential crack away from the critical beam flange region. The fracture demands from our proposed backing bar detailing are compared with the conventional backing bar detailing, and what we see is that the fracture potential is reduced by more than 6 times, and fracture in the beam to column connection is not expected even at 6% lateral drift demands. These conclusions were also confirmed by a series of parametric analyses that are not shown here in this talk due to brevity. To validate the proposed bevel backing bar configuration, we conducted full-scale beam to column connection experiments. And the primary objective of the experimental program was to enable the stable hysteretic response in the connection through panel zone shear yielding that was targeted to 15 times the shear distortion at yield at 4% story drift ratio, and therefore a delayed beam local buckling was expected to at least 5% lateral drift demands. A second objective of this testing program is to utilize the proposed bevel backing bar configuration I explained in the previous slide, and we kept it intentionally in place after the execution of the complete joint penetration welds in the beam flange to column face connection. The interior beam loaded beam to column connection was tested horizontally as shown here in this figure. 2 displacement control actuators imposed the lateral loading in the steel beam ends, and these were adjusted to the beam ends through the aid of adapter plates. And the pin connection was realized in the column north location as you see it in this figure. And with regards to the column south location, an hydraulic actuator was imposing a constant compressive axial load that equals 2% the axial load capacity constantly throughout loading. Also, the beam to column connection was supported laterally by a system that was designed according to the American code. To measure the experimental variables of interest, an instrumentation plan that includes 171 channels was employed, and this included strain gauges, linear variable differential transducers, string potentiometers, and rosette gauges. Due to time brevity, I will show the experimental results of only one specimen that was subjected to the standard symmetric cyclic loading protocol of the American and also the European provisions. And this loading protocol was applied so that the connection performance is assessed comparatively to the American and the European pre-qualification criteria. Here we show the test results. On the left side, left top side, we see the global view of the beam to column connection, and the left bottom side, we see the beam views and also the panel zone view. On the right-hand side top, we see the connection response in terms of column shear force versus story drift ratio. And the right bottom side, we see the panel zone hysteretic response, as I also showed before a couple of times. At lateral drift demands shown here as posed in this video of 2%, which is characteristic to the design basis earthquake event. The onset of panel zone yielding initiated at that point, and also we found traces of beam yielding in the beam. However, there was no identifiable damage in the proposed backing bar geometry. Moving forward to higher lateral drift demands, at 4% story drift ratio, with representative of a maximum considered earthquake event with a return period of 2,475 years. There was no incidence of beam local buckling, and there was also no damage in the proposed bevel backing bars. The panel zones reached 10 times the panel zone shear distortion at yield, which is less than the target we reached for the experimental program. And finally, at this drift level, the pre-qualification criteria of the American code as well as Eurocode Annex E are satisfied. Upon further loading, the onset of beam local buckling initiated at 5 to 6% story drift ratio. And even at this lateral drift demand, there was no, identifiable damage in the proposed beveled backing bars. Here we see that at 6%, there is some mild local instability in the beams, and there was some trace of backing bar yielding without any crack initiation or propagation in that region. And also, at this drift level, we reached the targeted panel zone shear distortions of 15 times the panel zone shear distortion at yield. Note here that after 6% story drift ratio, we continued loading the specimen because we just wanted to identify the ultimate failure mode of the beam to column connection that could be potentially important for collapse. However, the performance of the connection does not matter practically anymore, since for such lateral drift demands, the P delta phenomena of the moment resisting frame controls the seismic response. At the end of the 9% radiance amplitude, the test was terminated because of substantial loss of the load carrying capacity. Scanning electron microscopy in the test specimens highlighted that the failure mode involved ductile crack initiation and also propagation due to ultra-low cycle fatigue. And here we saw a characteristic sample of the scanning electron microscopy in the middle figure, obtained for the column flange fracture surface near the beam web centerline where fracture initiated. And from the oblate shape of the dimples, it is confirmed that fracture was caused due to ultra-low cycle fatigue. The performance of the bevel backing bars that we proposed previously is also highlighted in this slide due to macro etching that was extracted again from the beam web centerline. And this indicates that there was no crack initiated from the weld root of the bevel backing bar, even at lateral drift demands exceeding 9% radiance. And this gives credit to the proposed bevel backing bar design that practically minimizes the fracture potential in that region. The remarkable performance of the proposed connection is also highlighted in this histogram, where we compare the performance of past research in terms of achieved lateral drift demands. And what we see is that available connections in literature withstand 2 to 7% story drift ratio, contrary to the proposed connections that exceed 8% story drift ratio without any strength degradation. Finally, to investigate the existing concern that an elastic panel zone design may compromise the seismic stability of steel moment resisting frames, we conducted system-level simulations. In specific, we designed 32 steel archetype buildings for the high seismicity region of urban California. And this typical plan view is shown on the left, where on the one side we see that we have a steel special moment resisting frame that is analyzed as part of this study. And the other direction we have special orthogonal concentrically braced frames. 4, 8, 12, and 20-story buildings were designed, and both for 3 and 5 bays were considered in the moment resisting frame. And with regard to the panel zones, we targeted the panel zone design to 1, 4, 10, and 15 times the shear distortion at yield. And note here that the last two values violate the current seismic norms. We made all these designs, and they're available publicly, and you can find the design summaries in the given QR code on the top right side of the slide. To model the panel zone shear response, we utilized a typical parallelogram modeling approach proposed by Gupta and Professor Kravinkler. However, the panel zone hysteretic response is represented by our recently proposed panel zone model that I described before, since this is valid for high elastic panel zones and also for column sections with thick flanges. Referring to the beams and the columns, the modified Ibarra Medina Kravinkler proposed by Professor Lignos was employed. And what we observe here on the right side is that the global response of the connection is predicted accurately utilizing this modeling approach. And the same is also evident for the local panel zone response. Due to the highly inelastic panel zone designs, we explicitly consider the fracture potential in the connections, as described in the bivariate log normal distribution that I also shown before, that is shown on the right side. So what we do in the analysis is that at each time step of the dynamic earthquake loading, we calculate the fracture potential for all beam to column connections by considering the panel zone shear distortion and the story drift ratio at that time. So if the calculated probability of connection fracture exceeds the threshold that we set, then we assume that the connection loses its moment carrying capacity, as characteristically shown in the middle of this slide. Nonlinear dynamic analyses were conducted for all 32 steel buildings based on the 44 far-field ground motion of FEMA. And what we saw here in this slide is the probability of collapse of the moment resisting frames over 50 years in the vertical axis. And the horizontal axis, we see the targeted panel zone shear distortions of 1, 4, 10, and 15 gamma Y. Based on the collapse fragility curves and the hazard curves, we calculated this probability of collapse in 50 years, and we compared with the threshold, the reliable limit of the American code, which is 1%. And what we see is that conventionally designed moment resisting frames with elastic panel zones on the left side of this plot does not achieve this limit, contrary to our proposed elastic panel zone designs that pass this limit. This example is of the 3-bay moment resisting frames because this design utilized deeper beam sections that increase the fracture potential in the connections. Finally, engineering demand parameter hazard curves are developed as shown on the left slide, on the left figure. So on the vertical axis, we see the mean annual frequency of experienced targeted engineering demand parameter, where in this case we saw as an engineering demand parameter the residual story drift ratio of the moment resisting frame at the end of the dynamic earthquake loading. What we see here characteristically for the design basis event is that residual story drift ratio decreases by up to 30% once we allow for inelastic deformations within the panel zone. And on the right side of this slide, we see that the same tendency actually exists for all 32 archetype steel buildings that we designed. And this is particularly important from a building demolition standpoint that is controlled by the residual story drift ratios. Finally, engineering demand parameters for the number of beam local buckles were also developed. And what we see is that conventional design moment resisting frames achieve 3 to 12 beam local buckles per MRF for the design basis event, contrary to practically 0 once we allow for inelastic deformations within the panel zone. It should be noted in this case that the fracture was not evident in the design basis event as well as the maximum considered earthquake event. And this is particularly important from a structural repairability point of view, since beam local buckling is delayed once we allow the panel zone to participate in the earthquake dissipation. To summarize, we proposed an updated robust panel zone model that is accurate for high aspect ratio panel zone geometries and also thick column flanges, and also for high inelastic panel zone shear distortions. Then we proposed a welded moment connection typology with bevel backing bars, so simplified weld details and also balanced panel zone design that is able to sustain lateral drift demands of 8 to 10% radiance, with panel zones reaching even 30 times the panel zone shear distortion at yield. And these connections experienced local buckling at lateral drift demands higher than 5 to 6% radiance. And what we saw is a consistency in the failure mode that involved cycle fatigue. Finally, the system level simulations showed that once we target the panel zone design to attain 10 times gamma y, the residual story drift ratios reduced by 30 to 50%, and beam local buckling is practically not evident, and same applies for the beam local beam flange fractures. With that, I would like to thank you for your kind attention, and of course, we are open for questions at the end of this seminar.
Thank you, Andronikos, for the great presentation. Yeah, just a reminder for the audience, you can type your questions in the chat and we will address them after Nenad's presentation. So Nenad, over to you.
No, thank you, Stamatina. Can you guys, can you hear me and see my screen?
Yes.
Oh, perfect. Okay. Well, first of all, thanks everyone for joining, and I also echo and thanking the organizers, so Marco and Stamatina and everyone else for inviting us. This really an immense privilege. And I also want to, well, say that I have a really great but also ungrateful job, because the bar has been set high by both Andronikos and Dimitros, but also by previous speakers in these seminars. I've watched some of those. Those are always great. And then for all of you joining live, because this is like a lunch meeting, I assume you guys have had tasty lunch so far. So I may be competing with, potential food coma getting induced while I want to discuss some, statistics stuff. But I promise I'll do my best to learn new stuff. This work done in collaboration with Prof. Dimitros Lignos and also Prof. Alexander Alahi from EPFL, as well as Andy today. And the title is Data-Centric Machine Learning in Earthquake Engineering and Surrogate Modeling of Steel Moment Resisting Frames. This is a bunch of words. They're kind of hypey and sound fancy, but I'll try to unpack that nicely as we move through the presentation. So what is this talk about? Well, it's about steel structures, as this one shown on the left here, and specifically looking at this collapse limit state. So as it, as the structure is being pushed to very extreme, situations such that it induces collapse. And we want to understand that by looking at, its performance under a number of earthquake ground motions. And you can depict that in form of these collapse fragility functions, which are depicted on the picture on the right, where the vertical axis is showing the probability of collapse, and then the horizontal one is one of the intensity measures used in earthquake engineering, which would be the spectral acceleration at the fundamental period. And you can see this line is kind of a bit jaggedy. This is because this is an empirical cumulative distribution function, or ECDF, meaning each step along this line represents collapse response due to a single ground motion, meaning you have to compute a lot of these responses to trace this curve, and that's numerically, very expensive. So the idea here is, can we, in a way, efficiently estimate these collapse fragilities using data-driven approaches, efficiently meaning with less numerical effort. So that's what the talk is about. What the talk is not about, it's not about using machine learning to replace physics-based numerical simulations. No, that's not what it's about. It's actually based on physics-based numerical simulations, but then you leverage that data in a wise way, such as Dimitros had said. Okay, so up front, I want to just point out that this bulk of this talk is based on this reference here, which we published recently in the Earthquake Engineering Structural Dynamics Journal, specifically in a special issue on AI and data-driven methods in earthquake engineering. And I want to thank our sponsors, this National Science Foundation, for this. And so there's a lot of details in this paper, which I'll refer you to. So I want to unpack all of that in the presentation to keep it in a manageable and easily consumable format. And so to get us started, our roadmap will be first like this. First, I'll review some concepts related to seismic collapse risk quantification. And the reason for this is that I assume you guys are sophisticated audience, but not necessarily specialized in every nuanced detail related to this. So we'll review some of the important concepts there, and then move into this quote-unquote data-centric machine learning portion. And finally, and with a case study, just kind of showcase why you may want to consider some of these things. Okay, so that's the plan. So let us get started with the seismic collapse risk assessment 101. So collapse risk assessment, we want to estimate collapse of a building, which is depicted here, let's say a structure depicted here as a building, this frame little doodle with story heights H1 and H2, so it's a two-story frame. And it's being shaken by this earthquake ground motion depicted as this blue seismogram on the left. Okay, so we take this structure, we shake it numerically, and we get some response. In terms of what we measure here is the so-called story drift ratio, which is the ratio between this differential displacement between the top of a story and the bottom of a story divided by the height of that story. And specifically, if we look at the maximum overall story drift, that's the SGR max that we're going to be looking at. Okay, so we take a ground motion, shake the building, and we get an SGR max. And then to kind of present this in a usable form, we can also look at this seismogram, which is a Bijelić line, and plot it into these intensity measures, which one here is depicted as spectral accelerations. So this gray line is the spectral ground motion spectrum. And one point on that line is indicated with this red circle is the spectral acceleration at the fundamental period. So if we plot this value of the spectral acceleration with which we are shaking the building on the vertical axis on the right and the story drift ratio on the bottom, we start to trace this curve, which we'll learn is called the IDA curve, or the incremental dynamic analysis curve. Okay, and so at this point, we've shaken this building with this ground motion, and it didn't collapse, and we got some story drift ratio. So what we do next is we kind of amplify this ground motion a bit, so we scale it by a little factor larger than 2. We get another SGR max, and so this is depicted by this increase in spectrum on the figure on the left, and we start to trace even more along this curve, and we repeat this. So the IDA is basically shaking the ground motion, the structure with the ground motion, is asking the structure, oh, did you collapse? And then structure says, no, I didn't. Okay, I'm gonna amplify the ground motion a bit more, and I'm gonna ask you again, did you collapse now? And so we do that until the structure collapses, basically it's toast, and then this intensity, lowest intensity at which it collapses, that's what we call collapse capacity. Okay. So now we know everything you need for this presentation, but just to summarize it, to understand the next parts of the presentation, but to summarize it, what we're doing here is we're taking this single ground motion and we're dragging it along this point, we're amplifying that, and each intensity asking, oh, did you collapse? Did you not collapse? And then we're tracing the IDA curves. And so we need to do many analyses, even for a single ground motion, but in fact, we also want to analyze a set of ground motions, which is depicted here with this collection of spectra. And what you in effect end up doing is you're not dragging only a single ground motion, but rather dragging or increasing the amplitude of this entire set. And so that's why this is numerically demanding. And also I just want to, again, repeat this anthropomorphized version of IDA. IDA takes a ground motion and asks your structure, hey, did you collapse at this intensity? And the structure says yes or no. And the reason I'm saying this will become apparent later, but basically the response is binary. You're saying either yes or no. And you need to ask many times, and the way you ask is basically this IDA is, based on numerical, you're solving numerically nonlinear equations of motion, and so that takes a lot of time. So one of the ideas here is, can we, do some of that, but also gain more information of that if we could kind of train a surrogate, or like a statistical model represented here by this function h of x, such that we can leverage the data we have to learn more about and effectively trace collapse without having to compute as many times. So just to summarize again, the objective is not to replace physics-based numerical simulations, but the objective is to reduce the data requirements for collapse risk assessment. Okay. So how do we do this? So this is the proposal. We get into this quote-unquote data-centric machine learning. And to get us started, I want to just say that probably all of you have heard about machine learning and big data. These are very hypey terms. And you could say this, this machine learning has been the king of the jungle, like this line here. And arguably, these tools have enabled people to gain fundamental insights into important questions. But at the same time, we probably don't want this, glorious animal as a pet, because for one thing, it can get tricky when it gets hangry. Now, hangry, this is when you're hungry, and then you're angry at the same time, and it's a vicious circle, because the more you're angry, the more you're hungry. And if you need to feed this animal, it needs a lot of data, then it gets tricky. So the question here is, can we actually preserve some of the qualities and benefits of having this beautiful animal, but have it in a more tame format, like this little Hello Kitty here? And so that's the idea. We want to reduce data requirements by leveraging domain knowledge. Okay. And I'll just take a step back to a study that I was working on when I was doing my PhD at Stanford. It's been quite a few years ago now, and I was looking at regional collapse risk assessment due to earthquakes. This is Southern California, just to get our bearings straight. Disneyland is roughly around here, and then this yellow thing is the San Andreas fault. And I was interested to capture the regional characteristics of collapse risk at each of these little triangles, which represent sites. And to do this, I was using these physics-based ground motion simulations depicted at this simulation or animation on the right. And one of the key points here was that we actually wanted to, capture all the characteristics and fine-grained characteristics, both of ground motions, which are physics-based, but also use physics-based numerical models for structures to understand. In other words, they're really numerically intensive to compute. So as an example, I've done this for a 20-story reinforced concrete moment frame. And so the idea was to study that, and there's different approaches we took, but at that time, I was at Stanford, everyone was talking about big data, machine learning, and so naturally you have to try some of that. So we did this as well, and so I ran about 1,900,000 nonlinear dynamic analysis of this building with different ground motions at different intensities to train, in this case, a very simple machine learning tool classifier, which is a support vector machine, which then enabled us to kind of compute this regional risk depicted here as probability of collapse in 50 years in a very efficient way. To give you some numbers, if you would want the same type of computation that's on this map and do it numerically for each of those ground motions, so at each of these 336 sites, there was about 500,000 earthquakes simulated numerically, ground motions. Take you about 5 to 10 years on a 20-node cluster, so 400 CPUs, 5 to 10 years. I didn't have funding for 10 years for my PhD, so in that case, this machine learning will really help, because once you train, you can get this results in 3 minutes on my Mac. But this is conditioned on you having this data, these 1,900,000 analysis. And you could say, well, that's not really big data. You say, well, but in our domain, where people use 3, 7, or 11 ground motions, to design buildings, that's a huge number. So the facts of life are, we typically don't have big data, but we can simulate, small data, and we also have domain knowledge. So is there a way that we can really kind of leverage that and kind of get insights into this? And this brings us to this domain-specific data engineering, which I'm going to unpack here in this one slide. And then following that, I'm going to show you more results. So what we're starting with is this initial training data that we get from IDA. So this is the collapse results that I've been mentioning. So this is what we have initially, and we can plot this on a graph where X would be, some inputs, so ground motion characteristics, so spectral acceleration, and the Y is the response you're interested in. And let's say we also know the ground truth to which we want to, compare something. That's what we're trying to get at. And this depicted on the right on this, ECDF plot of collapse probability with the thick black line, and then the dotted gray line indicates this initial training data that we have. Okay, so that's, let's say this is, you run your IDA and this is what you get. So now let's say we want to train some numeric, data-driven surrogate and fit it to the training data that we have. So we get this, dashed gray line, and let's say make predictions for the ground motions that are in the ground motion in the test set, or which represents the ground truth. And let's say we get something like this thick gray line, and you can see they doesn't really match the ground truth well. And so the question here is now, okay, what do I do now? And so one way to do things is to say, okay, you can do the model-centric approach, which is you tune these hyperparameters in your data-driven surrogate to try to improve the performance. But on the other hand, the data-centric approach is you say, oh, can I do something to the data to improve the performance? So I'm not going to tune the model, and I want to keep the data I have, but just leverage it in a better way. Okay, so that would be the data-centric part. But also you could say, well, can I just get more data? But that you could do that, and you would then say, okay, I have this small data, it's a little baby, but in fact, if I want to run more IDAs, that's going to be numerically expensive. So could we actually leverage this small data that we have and massage it in some way such that we get good big data? So we take the small baby and we kind of do something to it to get more representative data that then, if you add this, red dots to your initial training data and then fit a surrogate to that your prediction in the end ends up matching whatever, the ground truth is very closely. And again, solely by data augmentation, not doing any additional numerical nonlinear analysis. And so that's the main idea, and this is what we described in this paper, which we call this procedure the Automated Collapse Data Constructor, or ACDC. And so that's what I'm going to unpack in this talk further. And just for those of you interested, there's a really nice talk by Professor Andronikos on data-centric AI and other domains. So if you want to take a look at this video, I encourage you to do this. Okay. So let's now this is in a nutshell, but how do we actually do it? So the idea is I have some data that I ran, I have my ground motions, I run IDA curves, and from this, the ground motions will represent my input, and then the collapse response from IDA is the output. And I want to somehow, massage the data to get good data to train my data-driven surrogate. So the way I'm going to do this, I'm going to take these collapse capacities and plot them horizontally. So this is the same set of points you've seen already. I circled in blue. I just put them horizontally. And they're plotted on this clutter plot. I'll unpack it briefly. So the vertical axis represents the probability density. I just want to point out that these points here, the height at which they're plotted doesn't make any difference. They're just for visualization purposes. They just indicate where the points are in the terms of collapse capacity. Where the probability density comes in is in these histograms that represent the data, and then the log normal distribution fitted to the data. Okay, so that's you take the data, you fit a log normal to it. And so the question now is, okay, where should I augment the data? Where should I add this data? And this is what we call this augmentation range. And so one way to do it is that we said, okay, well, let's just augment in the range that's within plus and minus 3 standard deviations from the fitted log normal, because that's what you would expect to have 99% of your data if you trust this log normal distribution. Okay, and also on this plot, I showed these transition boundaries that we call. I'll explain them a bit later, but basically we place them here in a way that they cover about 90%, so plus and minus 1.65 sigma from the mean, such that that range is where you would expect most of your data to be. And just to hint at this, the idea is that in this range where you don't have data, that's kind of like a critical, it's a different situation here as opposed to where you do have data if you do augmentation. Okay, But just to say, okay, now we know we have our data and know where we want to augment. So the question is, how do we augment it, as represented by these red, triangles? Well, our proposal is just augment in a way that you get a uniform distribution between your initial training data and the augmented data. And so you can see in this region where you have a lot of training data initially, you don't augment as much, basically. Okay. So I know this is a lot so far, so just let's take a step back and I'm going to rotate this figure a bit to the right just to say where we're at. So this is the same figure as before. I'm plotting on the left the training data and on the right the augmented data, and the vertical axis the collapse capacities. And we have the augmentation range where we've done the augmentation. And let's just zoom in on this one point, which represents the augmented collapse capacity of 2G. So what I'm saying here, I want a ground motion that will cause collapse at 2G. So I know where I want it to collapse my structure, but the question is, what should be the ground motion properties that cause the collapse of structure at 2G? And so how could you do it? Well, basically, our proposal is, well, look at whatever the neighbors are doing. So I'm circling here the neighboring ground motions, shown in gray. And these ground motions cause collapse in the vicinity of 2G. So probably, similar statistically consistent, ground motion property would cause collapse at 2G. That's the idea. So how to do this? Well, let's just plot these gray spectra of neighboring motions on the right. And you've seen this representation already when I was describing the IDAs, where you're, dragging this set of spectra along at the fundamental period. So they're pinched at that. They all have the same value at that. And for those of you who know this or have seen something, you're probably reminded of this concept of conditional spectrum, which was introduced by Professor Baker 10 years ago. If you haven't heard about it, don't worry. Just explained it in a nutshell. So the basic idea of the conditional spectrum is that it gives a statistical description in terms of a distribution of ground motion properties conditioned on all of them having the same value at a certain period. So all these ground motions have the same value at this fundamental period, and the conditional spectrum approach gives you information how to construct ground motions that would have the statistical distribution. Specifically, come up with the mean, and then percentiles here describe the variability around it. And underneath all of that is the multivariate Gaussian distribution, for those who are familiar here. And now the key part here in our proposal is that we don't just construct the conditional spectrum equally weighing all the neighbors. We actually put the so-called Gaussian kernel centered at the point where we're doing the augmentation, so that the weights of individual neighbors are proportional to the weights from the Gaussian kernel. And this is the so-called Gaussian smoothing approach. And so we take this bandwidth called H, which we tune. You need to figure out how wide to make this bandwidth. And there's a formula for optimal bandwidth if your data is normally distributed, but here we use cross-validation to kind of tune the bandwidth. And so once you know this, you create the conditional spectrum, which again, I'll just repeat, it gives you a statistical distribution from which you can sample a realization of a ground motion as indicated by this red curve, which then we say, okay, that's going to be the corresponding ground motion properties that belong to the point which I'm augmenting in the end. And you see, so we have a full circle. We started at the point we're augmenting in 2G, and we now have the corresponding ground motions that are the ground motion that's statistically consistent with the data you have from your training set, and that you assign to your augmented point. Okay, so that's a lot for now. But the key takeaway messages that I want to just emphasize here is that first, this collapse data constructor is surrogate agnostic, meaning I didn't mention any neural net, any regression tool or whatever inside. So it doesn't depend. It only depends on the data. You can also tune this bandit automatically, which I called an AC/DC auto tuner, which I thought would be cute. And then the data can be used both for interpolation, where you have the data, and then those regions where you don't have a lot of data. Now, details for this are in the paper. If someone has questions, I can explain that a bit later, not to muddy the presentation too much. But also, one important part what I want to mention is that this can be applied for both the regression as well as the classification setting. And what I mean by that is, if you look at this figure on the bottom where we have our ground motion and our collapse capacity because here that's what we get from IDA. You can say, well, in this format, I have a set of numbers which represent the ground motion. That's our spectra. And then collapse capacity is again a number. So if I want to predict this, this is a regression setting for those of you know. Set of numbers, and I'm going to map it to a number. Alternatively, you could say everything above collapse capacity will cause collapse, and everything below will be non-collapse. So you can also pose this as a binary problem, which I was alluding to by IDA actually asking the structure, do you collapse or not? And so this part is also in the paper, but we call it the data-driven collapse classifier. And I just mentioned it here, such as you know that moving forward, that's what I'm going to be using. Okay. So that's it for the second part. And now for the case study. So basically, I want to show you why would you even want to care about this. So these, we're going to, for the case study structures, we're going to use the steel MRF designed by Dr. Andronikos, Andy. So I just say thank you, Andy. And in the paper, we've analyzed, show case study for the 4 and 8 story MRFs. And we have another paper for an upcoming conference where we've pushed it a bit further, also including the 4, 8, 12, and 20 story MRFs. The results I'm going to show here are for the 8 story MRF. Okay. Now our ground motions that we start with, it's going to be the FEMA P695 far field set, 44 ground motions, as well as the spectrally matched long duration set. So this is depicted on the left on the scatter plot, where this is the ground motion duration, significant duration. This is SA ratio, and just and then we have a test set for about 340 ground motions, which are plotted in gray, and I now overlaid the whole NJ-WAYS database just so you see that's kind of roughly representative of the whole set. And just for the sake of completion, here's the spectra, an unscaled and scaled format for both the training set and the test set. Okay. And then we took these ground motions, we analyzed them, get IDA results as shown here. And so when we have this, now we want to do this, data augmentation and data-driven predictions. So a couple of information for this. What surrogate will I be using? Here, I'll show the results using the extreme gradient boosting, XGBoost. Why? Because this particular tool, people like it, so it works well. Okay, that was the main reason. But the key part is here, we're going to use a data-centric approach. So here's what we do. We take the XGBoost and use its default setting as you find it in a Python package, version 1.3.3. And then we don't change those hyperparameters. We just take it as is and feed it the data. The only difference in performance will come from augmentation or no augmentation. Okay, that's the key thing. And then in terms of predictive feature, all of these are based on intensity measures. In this case, there's 112 of them, including spectral accelerations, averaging, spectral ratio durations, but also these filtered incremental velocities. Basically, all the IMs people like when they find meaningful when they discuss collapse, sudden collapse. Okay. So now, finally, for the results. Shown on the left is the strip plots like you've seen. We have the observed data we start with. In the middle is the augmentation I do using AC/DC, and then on the right is our test set. Now, to make this problem harder, actually, we removed the 20% of the training data from this bottom part, which actually shows the lowest part of the collapse fragility, which then implies that the augmentation here will have to be done using extrapolation because we don't have any training data there, but also predictions will have to be done in a region where we don't have training data. Okay, so here's the result. You've seen this figure before. We see the ground truths, the initial training data and dotted line, and then the prediction of an XGBoost classifier with no augmentation. And if we apply the augmentation, we see that the problem is in the region where we don't see any data, because you see the predictor can't predict anything where it hasn't seen data. That's it's what's tripping it up. But if we add the AC/DC augmentation, then we get a much better predictor in this region. So that's kind of pretty cool here. But one other factor I want to leave you with is we've done this with XGBoost on the right, but we also tested a neural network, which is a completely different, surrogate, and you can see equal level of performance. So pretty cool. So the idea being that this is a surrogate agnostic methodology. It doesn't matter if it's neural network, XGBoost. You use what you really like. And then just to, in terms of, benefit and predictive capability, if we use only the initial training data and fit this neural network, the error in this error metric called mean Young frequency of collapse is about 45%. And then if you add the augmented data, the error reduced to about 4%. And again, just want to stress, there was no additional nonlinear analysis, no additional IDA was done, solely by massaging the data and augmenting it using the AC/DC procedure that I've shown. Also, final slide, our initial training data here contained 70 points, meaning 70 collapse capacities obtained using IDA. And past studies that we've done and other people suggest, well, you need 40 or more ground motions to get robust collapse predictions. So what we did actually is also take 16 data points, and we trained a neural network with 16 points using this procedure with augmentation, and we get performance such as shown on the right, which is pretty cool. Takeaway being, you do not need big data. They have been lying to you. All you need is, of course, love, and then second, you need a robust numerical model, and then say 20 or so ground motions that you analyze with that, and then leverage this type of thinking. Okay. And so just summary slide, takeaway messages. Data-centric approach is worth considering. Not many people mention it, so you may, if you're working this, may consider something like that. At the same time, the data augmentation is not a panacea that that obviates any considerations of ground motion selections or something like that. So you still need to be careful and smart what you're doing. And also, big data is not paramount to effectively leverage machine learning tools for assessment of collapse induced by earthquakes. Okay, so that is it from my side. Except we also have some shameless self-promotion. If you liked the presentation today and the things you've seen from ResLab, well, then there's good news for you. There's the World Conference incoming soon, and Professor Lignos has 4 sessions there dealing with structural steel structures, experimental testing, high fidelity numerical simulations, and then there's 1 additional session on this type of machine learning. So, hey, we're looking forward to seeing some of you there. And as to quote Professor Dimitros Lignos, it will be #glorious. So hope to chat somewhere more. But with this, I just thank all of you for your attention. Thank again the organizers. If you have any questions, feel free to ask in the Q&A or shoot us an email. Always happy to chat. Thank you.
Thank you, Nenad, for the very informative presentation. It's not self-promotion, it's sharing knowledge, and that's why we're all here today. Before we open up the session, quick Q&A, I wanted to thank all of you for being here with us today. We really appreciate the effort you put, making it here and presenting some of your work to us in a compacted form. So let's open up the floor for any questions. I can already see one, but I invite our audience to either type in the chat or raise your hand, unmute yourself and ask it. So first one from James. I can hear somebody wants to ask something. No, okay. First question from James regarding Andronikos' presentation. Is there any risk in adopting the proposed methodology could result in beam failure before column failure, which could be a less desirable collapse mechanism?
So yeah, thank you, Stamatina, for posing the question. Actually, yeah, that's a good question. And what we have seen from work that we have done both in the system level as well as in the connection level, we don't see this as being an issue. And actually, we have looked at over more than 30 connection configurations with variable geometries, with different beam depths, column depths, realistic seismic designs. And what we have seen is that the response remains consistent up to at least 8%. So yeah, we don't see this as being an issue to what we propose.
Okay. It's not written in the chat, but I've received 3 messages. Not sure why people became shy asking themselves, but people have been asking about the link to your experimental data. I know you've given us the QR codes, but since there will be a delay in uploading the presentation, is it easy for Andy or Professor Lignos that you put a link in the chat for the audience?
Yes, I can. In fact, I can type it right now. So here you are. And I just need to say that because this is something we released recently, pay attention at the top of the, let's say, websites, depending on what you click. If it says under construction, don't believe what is there. There is going to be some updates soon, but if it doesn't say under construction, it's pretty reliable. And also note that something we didn't point out, some of the engineering-oriented models we've released, you are going to see also in the new Eurocode 8 Part 3, which is the seismic assessment of existing structures. So the web-based tool could also help interpret some of these models, see if your benchmarking is done correctly and so on.
Thank you for the link. Next question in the chat. Why was the use of continuity plate avoided in your experiments, Andy?
So yeah, I didn't go through these details, but this is absolutely a great observation and question as well. By the seismic design norms, we were allowed not to use continuity plates since we utilized thick column flanges in our design, and therefore localized deformations in the column section were not expected to be that high. But what we know is that practitioners typically would even use continuity plates in this case. But the reason why we didn't use continuity plates is to actually be less conservative in what we want to apply, because the use of continuity plates reduces the localized deformations in the beam flanges, and therefore the fracture potential increases. So what we did against what we wanted to show, and which means less conservative than what we wanted to show, we avoided the usage of continuity plates in this experimental program to strengthen actually the outcome of the experimental results.
Thank you, Andronikos. Next question is for Nenad. Regarding the data-driven approach, whether modeling uncertainty is incorporated as it significantly affects collapse capacity and increases the spread of the data points.
Yeah, thank you for the question. This is an important question. The short answer is no. This one considers uncertainty due to ground motions, but there's a good reason for this. The reason is that, as you said, right, very nicely, is that it increases the dispersion. So when you're dealing with the statistics, there can be a tendency to hide behind the statistics because of a lot of dispersion. So we really wanted to first zero in on the cases where we have, no modeling certainty, meaning structural model is fixed, conditioned on like 4-story, 8-story, 12-story, and 20-story, and then once we solve that, bring in some of the other important questions that you point out here. So thank you so much.
One more question in the chat from Ahmed. Hi, Ahmed. Thank you for the well-structured and easy-to-follow presentation. Ahmed, do you want to come off mute and ask it yourself?
Yeah. Ahmed,
sure,
Ahmed.
why not? Right, it's a really nice presentation, yeah, for sure. It's good to catch up with what the group is doing at EPFL. So yeah, I'm already familiar with what
he's biased. He's biased.
Yeah. So I'm biased towards Andy, so that's why I'm trying to address the question to Nenad. So yeah, so I think you skipped this in your presentation, but I think you have done it because I skipped through the paper quickly. So yeah, so my question pretty much like you chose like a number of features in your model to predict the collapse. So again, did you observe like which of these parameters, like seismic or engineering parameters, that were controlling the classification? And yeah, this, I assume it does, agrees with our understanding of what causes collapse.
Yeah, thank you, Ahmed, for great. Yes, so indeed, we did do that, and we didn't fit it into the talk not to overburden everyone too much. It is in the paper. We use model interpretation using the so-called SHAP values, for additive explanations of this type of models in data-driven models. And so overall, yes, it agrees, and there's a reason why people have been studying this for 40 or more years and figure out these patterns on their own, human pattern recognition. But we also were able to, we introduced one additional ground motion intensity measure, which is kind of like our per-dependent duration, which kind of showed up to be also kind of important. So there's things to be uncovered there as we move forward, and especially this small data setting, but especially if you do big data, then that could be interesting. Thank you for the question.
Okay, just to follow up very quickly. So yeah, machine learning, like we see lots of these papers coming, and they are all, as you mentioned, yeah, it can solve like some problems that are very hard to solve otherwise.
Yeah.
But the question is like how to package this for other people to use. So do you have this as a function that somebody can use? Because otherwise it's very hard to to provide the black box directly for others to implement.
Yeah, this is this is an important consideration. Like, how do you bring people aboard? How do you people educate them? And also, I'm a nerd for these things. I would say, how do you help people fit linear regression? Well, they do it many times, and then they learn how to, but you're correct that having, robust scripts that would do this would be very beneficial. And then if people adopted learning from that, and so for sure, sharing code and results, which, we're doing. So, and then happy to, chat with anyone who tries this out and has any questions, issues, or
So do you have an user end, something for the users to use directly to for the ACDC model?
So that part, it is currently in a state that is not robust for most user friendly, but we're working on it, and it'll be posted on GitHub, and so then people can test it out and have it'll be a function for ACDC, and then a separate thing is how do you train a surrogate and all of that. Those are different issues, but I agree with you that there needs to be sensible approach to using these tools and kind of learning how to understand that, what you've done with Earl and all these other things that are tremendously useful when people can leverage directly. So something that for sure need to address.
Well, thanks a lot again for the great presentation and the great acronym as well, which so very nice. All right. Thank you again.
Couple of comments in the chat giving compliments for the presentations and for Professor Lignos. I can see one raised hand. If the person wants to come off mute and ask potentially the question.
Okay, can you hear me? Okay, first of all, thank you very, very much for such a comprehensive, such a series of comprehensive presentations, especially the second one, which still is some kind of dark side of the moon up for us. But my question really governs the work of Professor Skiadopoulos. In the Dr. Skiadopoulos, sorry, in the formulation you showed for calculating the panel zone shear yield capacity, I didn't saw any indication for accounting for the effect of column axial force, especially when the panel zone become completely yielded. We know that the presence of axial load will shift the the kinking distortion significantly. So this is the one thing. The other thing is maybe become more philosophical, is that your proposed methodology may seem like an alternative for rehabilitating of WFW connection by just shifting all the plasticity into the panel area. The point is we cannot provide the kind of balance yielding both in the plastic hinge and also in the panel zone area, because the strain hardening rate in the panel zone area is a lot less than the plastic hinge. So if the panel zone yields, we will not have further yielding in a plastic hinge. So don't you think this kind of excessive distortion in the panel zone will lead to some kind of instability, as Ibarra and Kravinkler in 1999 indicated? Thank you. Thank you very much.
So hello, thank you again for thanks for this for these two questions. They are both very good. So with regards to the first point, yeah, I didn't have the time to elaborate more on this. But if you refer to the journal paper we have written about the proposed panel zone model, we have actually looked at both constant as well as constant for interior columns, as well as variable axial load for which governs the end columns, for variable panel zone geometries, and also variable amplitudes of axial load. And what we saw is that the conclusion of all this study was that the von Mises criterion describes very well the reduction of the panel zone shear strength because of the combination of the shear to axial force within the panel zone. So this is exactly what we proposed in the panel zone model. We also looked at different double plate configurations, and how these affect the panel zone shear response, but that was again not part of today's presentation due to brevity. So with regards to the second point, I think this can be answered well from the system level simulations that we conducted. And it's true that the post-yield stiffness is lower in the panel zone once we allow for the panel zone shear yielding contrary to the beam. But what is also true is that there is no shear strength degradation in the panel zone contrary to the beam. And what studies from back in the day from Stanford University have shown by variable researchers is that once we have degradation is what really controls the P delta phenomena in the MRF response. And this is exactly what our system level studies that I showed in the end showed. Thank you again.
Maybe I can add just a couple of points. So the first thing is that what you saw in Dr. Skiadopoulos' presentation applies to new construction. So we haven't looked at retrofitted configurations, okay? Where there somebody has to look also some aspects on existing welds. So that's why I just want to clarify this. However, we have work in mind regarding what you say, particularly because we know that existing structures could have weak panel zones. And then the last thing I wanted to point out is that with what we propose, we don't try to remove the plastic hinging forming in the beam, but what we try to do is that we try to relax a bit the plastic deformations in the beam, but still have it participate. And with that, you can the frames or moment frames can accommodate much larger deformations prior to beam local buckling. So if you think about this, if you get a design level event and your beam buckles, most likely you're not going to demolish the building, but you still have to fix the beams. And in that case, if the panel zone participates a bit more, if we are only dealing with beam flexural yielding, most likely you're not going to do anything to the beams. So essentially repairability actions are going to be much less in that case. Okay, so this is just two clarification points.
Okay, I don't see more questions in the chat, and I'm mindful of the time. So I think it's time for me to thank again our speakers for the great presentations they delivered for Young Seced. And please do stay in touch and come back to present to us any future developments. Thanks a lot for your time. Thank you everyone for your attendance, and hopefully see you soon.
Thank you.
Thank you.
Thank you so much. Bye-bye.